So the last section is focused on electric circuits and other analogous systems. We'll focus primarily on the electric circuit stuff, but knowing that that can be applied elsewhere. The nice thing about this is now we're seeing some of the same models that we talked about in the first few sections being applied to a different scenario. Again, how many of you have done circuit stuff in physics already? Okay. So for some of you, this should be pretty easy. And you can help me out too, since my background is not as strong as yours is anymore. But we'll start with LRC circuits. So here you have your voltage supply emitting some current flow. And then we got one of these guys, which is a what? Which is an inductor. Good. And this is the symbol for a resistor. Good. And the last part of the LRC circuit would be the capacitor. Okay, so using Kirchhoff's second law, that states that the voltage drops the voltage lost as the current flows from the inductor, resistor into the capacitor is going to equal to what? Anybody remember? Voltage applied at the source. Which is where E of t is. Okay. And now we're going to see something very similar to what we've seen before. But let's kind of review, and for some of you, you may not know this. We'll examine the voltage drops across each one of these. Okay, so as it goes through the inductor, you guys remember what the voltage drops equal there to? I will just tell you what it is. L, the inductance, times di dt. Looks familiar or no? Okay. Maybe forgotten. How long ago did you do circuits in physics? Like yesterday? Across the resistor, you guys know that one? IR. Across the capacitor, that's 1 over C times Q. Q is charge. Resistance, inductance. This is in ohms. Units here are farads. The units for inductance, I want to say henries, right? Okay? Now, the one thing that we're going to use to simplify things a little bit is the relationship between current and charge. How is current related to charge? Good. dq dt is equal to current. So then this guy is going to get plugged in there. And now we have a differential equation that looks suspiciously familiar. If we add all these up, we get L. And then if we're looking at the first derivative of current, but we know that current is dq dt, then if we leave everything in terms of charge, what would this be? Second derivative, good. So d squared q over dt squared plus r, we're not going to use current, we're going to use dq dt, plus 1 over cq, and that's going to equal the voltage applied to the circuit, E of t. Yep. Okay, so this is the model we will be working with. If there is no voltage applied to the circuit, we say that the electrical vibrations of the circuit are free. Okay. So again, it's your run-of-the-mill second order equation. The auxiliary equation will be Lm squared plus Rm plus 1 over c equal to 0. So again, there's going to be three cases. If, let's see, the discriminant would be b squared, so r squared minus 4 times a times c, so that's L over c. So if r squared minus 4 times L over c is greater than 0, equal to 0, less than 0, we have the same systems as before. What kind of system would this be? Greater than 0, real roots. Overdamped, good. Equal to 0 was critically damped, and less than would be underdamped. Greater, over, equal, critically, less than, under. Easy to remember. Okay, in either case, or in any of these cases, when you start finding the roots, you do opposite of b, plus or minus r squared minus 4L over c, all over 2 times a. This is the key term. Because this indicates that all the solutions are going to start out with what term? If alpha is minus r over 2L, then what's the first thing we write down for our complementary solution? E to the minus r over 2L, good, times t. And then you have your other stuff, right? But as time goes to infinity, what happens with the system? Charge goes to 0. Okay, this term, no matter what we have going on in here, this term is going to get closer to 0, so eventually we say that it approaches 0 for the charge. And we're good to go. Okay? One more side note, and then we'll do a problem or two. If E of t equals 0 and there is no resistance, two things we want to say. One, you should be able to tell me. If there's no resistance, do we have any of this going on? There's no damping force. So this is going to be undamped. We say the response is simple harmonic. Okay? So that's the background that you need. Any questions so far? If you're not in physics, don't worry. It's not going to be hard. All right, let's try a couple problems. Let's say we have an LC series with no external force or voltage applied. We want to find the charge on the capacitor for time greater than 0, given an initial charge of Q naught and no current flowing initially. Yeah, it's like the voltage source applied to the circuit. Well, it's going to be a function of time because the voltage drops are going to change because those are related to time. Does that make sense? Okay, so what is the model going to look like for this? There's only one equation that we've talked about so far. It starts with an L. What comes next? D squared Q over dt squared. There is no resistance, so the only thing left is what term? 1 over CQ equal to 0. Okay? So let's find the solution. the auxiliary equation would be L m squared plus 1 over c equal to 0. Maybe we divide through by L. Take the square root after we subtract. So our solution will be what? Let's do the cosine term first. But yeah. Okay. So now let's use some of these initial conditions. We know that initially charge is Q naught. If you plug in 0 into the charge equation, sine term drops out, cosine of 0 is 1, so we just get C1 is equal to Q naught. Okay. If you plug in 0 into the derivative of charge, we know that's 0. And regardless of what derivative we get, here we get minus C1 root LC, or 1 over root LC times sine. That term's going to go away. Here we get cosine of 0. But regardless, the coefficient in front will cancel out. C2 has to be 0. Okay, so with that being said, we have our general solution. It's going to be Q naught cosine 1 over root of L times C times T. Okay, so we've done what they've wanted us to do. We have found the relationship over time for the charge of the system. If, this is the other thing they might ask, if we want to know current, which is I, right? How do we do that? Just take the derivative. Good. So since I equals dq dt, we just take the derivative. What's that? So I'll put the negative here, and then sine T over, looks good. Okay. I'm going to give you a problem to do. This is pretty much what the homework's going to look like, and if there were an exam question from this section, it'd probably be one of these run-of-the-mill questions. Okay, so again, we're doing some basic physics stuff, not anything intensive. We're just trying to look at some other applications besides springs. That we can use second-order differential equations with. Alright, so let's say we want to find the charge. Which again is Q of t on the capacitor in an LRC circuit when inductance is 0.25 henries, resistance is 10 ohms, and capacitance is 0.001. And let's see what else. Say E of t equals 0 initially. Initial charge is Q naught. And no current initially. So here's what I'd like for you to do. Find the solution for charge, and then write your solution in terms of one trigonometric function. You guys know what I'm talking about? Okay? So go ahead and try it. For the sake of the video, I'm just going to write the answer up here. Do not look up at the board.